A particle has velocity function, and it gives us our velocity function. We have it in component form: 3 minus t, 2t, 3t squared minus 4t minus 2. And I should note, I do tend to overuse component form. They don't always do that. Not everybody does that. So it might be the case, I haven't looked at the exam recently, but it might be the case that they may not write it in this form. They may write it as 3 minus t times I plus 2t times j plus 3t squared minus 4t minus 2 times k. These are the same thing. So be able to go back and forth. I just find it much more convenient in component form, because I just say, all right, I know I'm doing calculus on each slot, work the slots. Okay, so back to our regularly scheduled problem. What is the vector that points from where the particle is at time t equals 1 to where the particle is at time t equals 3? And this vector is the displacement. So we have 4 options. 1, 4, 3, minus 2, 4, 16, 2, 8, 6, 3, 5, 2, and 9 halves, 9, 3. All right. Well, you've had some time. Do you have an answer? C is correct. Great. Wonderful. So what's going on? So if you think of velocity, velocity is a rate of change. So if you think of velocity times dt, that's a little bit of change. And then if you think of integration, you're adding things up. So you're adding up little bits of change. And so that's the total change, the cumulative change. So it really is the integration from 1 to 3. And then you say, okay, well, we just integrate each slot. You evaluate, and you get 286. Good. Good. All right. Well, wonderful. All right. Good. We're getting better at these, right? We're peaking at the right time. Okay. So, thought for today. And it's that mathematics, it's built off of patterns. And it's important to be careful not to confuse coincidences with patterns. And I write down one of my favorite examples, which is you say, well, 16 over 64. Say, okay, cancel the 6's, right? And that's 1/4. Well, is it true that 16 over 64 is 1/4? Yes. Is it true because you cancel 6's? No. It doesn't work. If you picked another pair of numbers, it wouldn't work. So if you pick 19 over 95, what do? Cancel the 9's, right? You get 1/5. And is that true? Actually, it is. But so that wasn't the best example. But I'm sure I could find one where it didn't work. Is the punchline here. So the thing is, you have to be careful. And why do we care about patterns? Why is that so important? Well, in some sense, math is, you feel like there's always, I'm learning more and more math. So you feel like it's like this balloon that keeps expanding and expanding. And sometimes it feels overwhelming, like there's too much to remember. But when you have patterns, you can actually start to deflate the balloon a little bit. Because what happens is the patterns say, oh, these 10 different things fall into the same pattern. So I don't have to remember 10 different things. I have to remember the one pattern. And so that's how things stay manageable. So it is important to recognize patterns. Now you might say, well, how do I tell the difference between something that's a coincidence versus something that's a pattern? Well, coincidences work once or twice. Patterns always work. And in particular, in math, patterns are things that we can explain and justify. And coincidences are things that annoy our instructors. So that's sort of the idea. All right. So on to today. And if you've had Calc 2, a lot of what we talk about today is going to sound very, very familiar. And in essence, it's almost completely contained in this one sheet here. So we're going to talk about distance. The distance traveled along the parametric curve. So we have some parametric curve, r of t, and we're moving from time t equals a to time t equals b. And we want to find the total distance. Now, we've done this before. In Calc 2, we talked about lengths along parametric curves in 2 dimensions. So this is more or less just saying, okay, we're adding a dimension. And the punchline is the ideas, the underlying philosophies are still the same. So we start thinking to ourselves, okay, let's channel our inner Calc 2. Calc 2, what a fun class. You know, it's not always the funnest class when you're going through it, but we can always look back on it fondly and say, good times, good times. So our Calc 2 hat, what does it say to do? Well, it says if you're trying to find the total of something, and in our case, our total is total distance. Okay, so we're trying to find the total of something. Break it into parts. Okay, so you can imagine that perhaps we have some curve that we're traveling along. So here's our curve. You say, all right, let's break it into parts. So what we'll do is we're going to chop it up. And we say, all right, we're going to think of this instead of one big curve, we'll split it up into pieces. Maybe we'll split up into those pieces. So, all right, now that you've broken into parts, you estimate the parts. And the idea is you say, okay, well, let's estimate with things which are easy. In particular, things which are flat. So we would connect and say, imagine that I took this shape and I just connected with straight line segments at these points. And now I can say, okay, I can find that because I know how to add up straight line segments. And so I can find each individual straight line segment, I can add them up, and life is good. So that's our estimate. But then the magic of calculus says, let's do better. How do we get a better estimate? What do we do? Yeah, you split it up into smaller pieces. So if you now split it up into much smaller pieces, I don't know if these are much smaller, what happens is that it starts to look even more like your curve. Is it perfect? No, but it's close. And eventually, there's this notion of the limit, which is to say, imagine that you broke it up into really, really, really tiny parts. And in particular, as the number of parts gets very large, it's imperceptible, the difference between the actual one and the real one. All right, so how does this all work in practice? Well, we're after our length. So we're adding up our pieces. That's what the sum means. This is sigma for sum. So we're adding up our pieces. And now we say, well, we want distance between our pieces. So we use the distance formula. And we say, well, how do we find the distance between the pieces? Well, change in x squared plus change in y squared plus change in z squared. And then take the square root. All right, well, that's not so bad. So what happens? Well, we'll add in this thing called change in t. So I'm going to divide by change in t on the inside. Now notice this is being squared. I can pull out a change in t. Squared. Square root would mean there's a change in t in the denominator. That's why there's a change in t over here. This one cancels out with these downstairs. And now I say, well, change in x over change in time, that's another name for derivative. So x prime, y prime, z prime. And finally, as we refine, our sum becomes an integral. And we have the integral from our starting time to our ending time, the square root of x prime squared plus y prime squared plus z prime squared. And that is the magnitude of r prime. All right, and there it is. There's our formula. Good. And this, by the way, ties back to the very conclusion of last time. We said, well, what is this finding, this integral of the magnitude of r prime? And we said, come back next time. Well, we came back. We're here. And that's it. It's the length. All right. Good. Good. Now, I will tell you, they love length problems. So let's make sure we get good at them. We're going to do a couple of these. And today, that's it for the theory. Everything else is practice. Well, it's mostly it for theory. we'll do another quick derivation of this formula. If you don't like that derivation, or you want to remember it in a slightly different way, here's an alternate derivation. We say, well, let's think about the magnitude of r prime. We gave that a name, speed. Well, how do you find distance? To find distance, you integrate speed. So if you take speed times a small change in time, that's a small change in distance. If you add up your small distances, you get your total distance. And so it's the integral from a to b of the speed function dt. So this is a little bit easier to remember, or easier to say, oh yeah, that's why it works. Now you'll notice there's a thought bubble down here. There's this relationship, the square root of a squared plus b squared. It's still true that it's not a plus b. And I know it'd be so convenient if it were, but it's not. So you have to figure out a way to handle the square roots. Now, the big thing, but it's not the only thing, but the big thing is you're looking for something on the inside of the square root that you can work with. Oftentimes, it'll be something that factors into a perfect square, or something you can do a substitution. Sometimes they'll just say, look, just set it up. If you can set it up, life is good. All right, so let's try an example. Well, before the example, let's just check in on the theory. Do you have any questions on the theory? All right, then on to the example. So we have a particle, and it travels, and we're told it's parametric, this movement. The x-coordinate behaves like a half t squared, the y-coordinate behaves like root 2t, and the z-coordinate behaves like log t. And the question, what we're asked to find, is it says, find the distance traveled from time 1 to time 2. Okay, well, good. Let's see what we can say. So we start with our distance formula. Well, we could. I like to start with r. Let's just put it into component form. So half t squared, root 2t log t. And I want to compute this. So before I even start setting up the integral, I really want to spend time figuring out this magnitude of r prime of t. We're going to do a lot of stuff with magnitude r prime of t. We have today's lecture. We have next time's lecture. And that will also involve magnitude of r prime of t. So let's get a handle on that. So let's start with r prime. What is r prime? Okay, derivative of each entry. So in our case,
t squared root 2, 1 over 2.
Good, t square root of 2, 1 over t. All right, now the magnitude of r prime. So the magnitude of r prime. This is the hard part. Square root of the first entry squared, the second entry squared, and the last entry squared. So that's the square root of t squared plus 2 plus 1 over t squared. All right. So, we are thinking, we have to integrate this. Currently, our initial reaction is, ugh, that doesn't look fun. It's a very reasonable reaction. Say, okay, so let's think about this. We want to simplify. So in particular, if we are thinking about looking for a perfect square, if possible, this doesn't always happen, we say, well, perfect squares look like a squared plus 2ab plus b squared. So we start thinking about, are there natural candidates to try for a and for b? Is there anything that looks like a natural choice? So yeah, like this looks like something squared. This looks like something squared. And this, I can't help but notice, there's a 2. Suspicious. So let's see, t quantity squared, 2. 1 over t quantity squared. Now, if this is right, is it true that if I put t 1 over t, does this work? Does this match?
Yeah.
Ah, it's like it was meant to be. Nice. Okay, so this becomes the square root t plus 1 over t quantity squared, which is t plus 1 over t. We got rid of the square root. Woohoo! Yeah. That's nice. Okay, so now that we've done all the hard work, now we actually turn to the calculus part. Well, I guess we did a little bit of calculus along the way. We took the derivative. But now we've got to do the integral. So we're going to integrate from where to where? Yeah, we look at our bounds. 1 to 2. This time it gave us our bounds in terms of t. Sometimes it gives us our bounds in other ways. The magnitude of r prime, t plus 1 over t. So that's magnitude of r prime. And dt. So what does this integral become?
T squared over 2
Okay, t squared over 2.
from 1 to 2.
Plus, there's another part. Let's do that other part too. Natural log of t. It's not uncommon to see pieces that you started with showing up down here. That won't happen all the time, but it's not uncommon, from 1 to 2. All right, plug in 2. A half times 2 squared, 2. Log of 2, log of 2. Subtract a half times 1, a half, log of 1. Can we simplify any of these terms? Yeah, log of 1 is 0. Woohoo! Point. It's gone. Anything else we can do? Yeah, okay, 2 minus a half. What is 2 minus a half? 3 halves. Or for engineers, 1.5000. And log 2, which we can write as log 2. And we're done. That's it. So there we go. That's our distance. Now, quick observation. If we had gone a negative number, would we just be like, cool, let me keep going? Or would we be like, huh? What's our reaction if we end up with a negative number? Well, negative numbers means mistakes were made, right? Because distance is a positive measurement. So if you get negative numbers, you're like, something went wrong here. Probably went wrong in your integration. So check your work. And you can also even say, does this feel reasonable? Have I traveled far enough? All right. So that's an example. Any questions? Yes?
That yellow part where you have like the plus 2t times 1 over t.
Uh-huh.
What happens to that 2?
Well, that 2 is part of the 2ab. And so if you're looking for a square, if you see 3 terms, you probably think, okay, this has the potential to be a square. And you start thinking like, okay, what's my a, what's my b, what's my 2ab? Well, if there's just a single 2, it's like, that's probably my 2ab. And I just have to figure out, what's the a and what's the b? And if I multiply them together, does it give me what I need?
What happens if it's not a perfect square? Like, what do you do? If it doesn't turn into the t?
Right. Well, a couple of things can happen. Sometimes you'll have like a high power of t on the inside. You can pull that high power of t out, and then you can do some kind of substitution, and then you can make progress. And there's other things that can happen. But if we ask you to find an answer, I won't say it will always factor into a perfect square, but you always have a way. So keep simplifying. The real goal here when we're computing the magnitude of r prime is to say, can we make this expression so simple that we can actually integrate it? Because integration is hard. I don't know if you've ever noticed that, but it's hard. And we can only integrate a couple of things. So our goal is to say, keep chipping away until you get down to something that you can work with. And like I said, if we ask you for it, there will be a route. So perfect squares or a type of substitution. There will be something. Keep trying. Try something, right? As we said, try something. If it doesn't work, try something else. All right. Next problem as we move along. So, you're given r of t is 1 minus t squared minus 1, and t cubed. Find the length of the curve from t equals minus 1 to t equals plus 1. And there's a hint. The answer is not 0. Well, that's a strange hint. I don't know why they'd give us that hint. Now, does it seem reasonable to say that the answer is not 0? I mean, certainly time has changed, but that doesn't mean position has changed. Where are you at time negative 1? Can we figure that out? 0, 0, minus 1. Where are we at time 1? 0, 0, plus 1. So we've definitely have moved. And if you've moved, well, you have to have moved some distance. There's no secret Mario warp tunnel that jumps from negative 1 to positive 1. Okay, so the answer is not 0. So I gave you a clue. But let's talk about the idea. So what's the strategy here? Well, we find r prime, sure?
Oh, so you find the r prime, you do your distance formula, and
Right.
you ended up with 9t to the 4th plus 8t squared in the square root.
Okay, so I think pretty much everybody got there. 9t to the 4th plus 8t squared inside the square root. Good, good. And then
Then you take t out.
take the t squared out of the square root. This is where the deviousness happens. When you take the t squared out of the square root, what does it come out as? Absolute value of t. Because the t squared is always positive, the square root of t squared then will also always be positive, so it's the absolute value of t. So what's happening, the reason you got 0 is if you forgot the t, you have a function which has symmetry, positive on one side and negative on the other side. It exactly cancels out. But with the absolute value, you say, well, hey, instead of going from negative 1 to 1, because there's perfectly symmetrical, go from 0 to 1 and double it. So this is, you have to be careful when you pull out things outside of an absolute value. So that's sort of the punchline here. But you had the right ideas. So then I think everybody was actually doing the integral right. It's just this one small detail I think that was catching people. You can do a substitution on the inside. So the square root of 8 plus 9t squared, that's what you have here. Set u equal 8 plus 9t squared. I always like to make the whole thing my u substitution. Go all the way. Then the du is 18t dt. Or 1/9 du is 2t dt. The reason I put a 2 there is there's a 2t dt. So 1/9 the integral from 8 to 17, u to the 1/2 du. I always like to update my bounds because whenever I do substitution for a definite integral, I always like going forwards. I never like to go backwards. So as long as I keep updating my bounds, it's always moving forward. So you integrate. That gives you your 2 to the 27th. And you evaluate u to the 3/2 from 17 to 8. So 2 over 27 times 17 to the power 3/2 minus 8 to the power 3/2. Good times, good times. All right. Well, that was fun. That was fun. So let's try another idea closely related to distance. And that's cumulative arc length. And what this means is it's the total length that you've moved along the curve, starting from some initial time. We usually start at time 0 up to our current time. So how far have we traveled along the curve? That's the cumulative arc length. Now there's an observation here, which is not too profound. It just says, if I take the derivative of s with respect to t, well, I can apply the fundamental theorem of calculus. Fundamental theorem of calculus says if I'm integrating, and then afterwards I take a derivative, I'm getting back to what I was trying to integrate. So it's the magnitude of r prime. We will mention this in our next lecture. Now, why do we care about this? Well, what this tells us, suppose we do know our cumulative distance function. So we have this way that you give me a time, I can tell you how far we've traveled. Well, we can now go backwards and say, well, let's change the way we travel along the arc. Or let's think about the way we parameterize the arc. And we can now, we'll say, instead of making it a function of time, we make it a function of distance. So how far along the arc that you've moved. And why do we care about this? Well, this gets into the question of, what can you tell me about the curve? So, in other words, I have this particle traveling through space. And I can think of it as moving along a wire. And I care about the shape of the wire. I don't care about how fast the particle moved along the wire. I just want the shape of the wire. So I want to remove this notion of speed, how fast I was moving along it. So by reparameterizing in terms of distance, then I say, okay, that's sort of a standard way to measure. So it gets us into the theory of how do we understand the curves, and that's going to be the topic of the next lecture. Now, you might notice that there's an asterisk here. Yes, we can do this in practice, but in practice, it's very hard. It's more useful to apply it in theory. But there are some special cases where we can do it. All right, so here's a nice case. We have the helix, cosine t sine t. Now, suppose for a second, let's test your memories here. Suppose we covered up the z part. So we just had cosine t sine t. What does that look like? It's a circle. In fact, cosine t sine t, that's the classic way to parameterize movement along the unit circle. So we have this unit circle. We start here at x equals 1, and we move around the circle. And we just keep moving, spinning around and around and around. So that's if we just ignored the z. But let's suppose we don't ignore the z. Okay, then what's going to happen? What's happening to our z coordinate as we change things here? So, as t increases, what happens to z? It increases. It's just going up. So if you were to take the z-axis and grab it so you could look straight down it, what you would see is this curve. So you would see a circle spinning around. But if you now say, okay, but what is it looking like in space? Well, it's this shape that just keeps going up and around. So this is why we call it the helix, because it looks kind of like a helix. If I was better at drawing, you'd be like, oh, ooh, helix. But okay, this is getting worse. This part's okay. Look at this part. All right, the helix. Ah, wow. All right, yeah. Pretend I didn't draw this part. All right, so that's what we call it, the helix. Okay, so now we need to find s of t. So that's this cumulative arc length function. We're going to use t0 equals 0. So we say, okay, this is our r of t. So before we start going into the integration, let's spend some time, like we should always spend time, focusing on finding a simple way to write the magnitude of r of t. So, magnitude of r prime of t. My apologies. What is r prime of t? Sine t, cosine t, 1. Good. So what's the magnitude of that? Square root of sine squared Cosine squared, 1 squared. Does that simplify? Square root of 2. Okay, so then s of t, if we apply this formula, it's the integral from 0 to t of square root of 2 dt. Well, is that something we know how to integrate? Oh yeah, we do know this one, yeah. What is this integral? Square root of 2t, and then evaluate from 0 to t. Technically, we should have put a tau in here, but that's okay. We're amongst friends. Square root of 2t. So, there we go. So that's find s of t. We found it. S of t is root 2 times t. Woohoo! Nice! Yeah. But there's a second part. It says, well, reparameterize the helix as a function of s. So you'll notice here, this says s is root 2 times t. So to reparameterize means we need to solve for t in terms of s. So if s is the square root of 2 times t, what is t? Yeah, so we can solve t is s over root 2. So now, replace your t's in your parameterization with the new values which have s. So, this would become our cosine s over root 2, sine s over root 2, and s over root 2. Okay, so this is our reparameterization. We can call this our R of S. And I have a little bit of space here. So let's ask a quick question. Question. Where is the particle after we have traveled 5 units? How could we answer this question? And I probably shouldn't have chosen 5 because my 5s look too much like my s's. So how can we answer this question? Our particle has traveled not time length 5, distance 5. Where are we? Yeah, we're at s equals 5 because traveling 5 means that our cumulative length is 5. So this is just another way of saying, oh, hey, s equals 5, what's our position? This is how the problem could be phrased in a much more compact way. S equals 5, what's our position? So what do? We plug in s equals 5. And we get weird expressions. Cosine 5 over root 2, sine 5 over root 2, and 5 over root 2. But just because they're weird doesn't mean they're wrong. That's fine. Weird things can happen too. So, all right, so that's cumulative arc length. All right, let's see. Where are we at? We have a few minutes left. Oh, a few quick questions, I see. Yes?
Do you want to write that as a vector or a point? It's asking the position after 5 years.
I would say that in our class, we would be happy with either one. That's a good question. So I would say, that given our conventions, because we started with writing things as a vector, I would say you would be fine leaving it as a vector. Other questions? All right. Well, we do have a few minutes left. So we can actually do a proper multiple choice send off. Now notice you don't actually have to solve it. So you're like, oh, thank goodness. You just have to figure out how to set it up. So a particle travels along the curve. R of t, t squared minus 1, 2t, 4 minus t squared. Which of the following integrals gives the distance traveled from the point 0, negative 2, 3 to the point 3, 4, 0? So you have 5 options. So think about which one of these integrals gives the right answer. All right, our time's just about up. Do we have an answer? The answer is B. Good. So in this case, you could almost get it just from this first term, but also you might have to convert. So notice they gave us things as points. Well, if you have points, you have to convert to times. Well, use a convenient coordinate. In this case, the y coordinate is very convenient to convert to times.